Now when they found Pluto, they soon realised how small it was. Because it was so dull, so dim, so hard to find, it must be tiny. And it was. They've been able to measure it and they can see. It's much, much smaller than the Moon, as you can see. It's probably about maybe the size of Western Australia. So it's still pretty big, but as far as planets go, it's quite small. And now we know Pluto has at least 3 moons. Charon is its largest one. Charon is actually so big that rather than calling Pluto a dwarf planet, a lot of astronomers think they should call it a double dwarf planet, because the Moon is so big that rather than the Moon going around Pluto, they actually orbit each other. Pluto has the largest moon for its size. The Earth is next because our moon is quite a large percentage of the size of the Earth, but in the case of Charon, it's about 1/3 of the size of the whole planet. And I'll know a little bit more about Pluto in 2015 when New Horizons gets there. Heading there at the moment at more than 1,000 kilometres an hour. And it's been going there for a number of years now. And it will go past, take lots of photos of Pluto and the Moon, hopefully discover some more moons, and then it'll just head out into space. So they've only got a matter of a few hours. It's taken years to get there. And then they've got a few hours to take pictures and that's it. And then they hope by then there'll be another planet of some sort out there that they can divert it around. It has a little bit of fuel left that they can swing past something else. Now before they visited Pluto, they actually said to Clyde, when they sort of penciled in this mission, they said to him, because he'd discovered Pluto, they asked for his permission to visit the planet. So he said it was okay with him. I suppose he'd leave the lights on for them or something like that when they got there. Because he's died since then, they actually put a few hundred grams of his ashes onto the New Horizons spacecraft. So physically part of the discoverer of Pluto is actually heading towards Pluto, towards his planet. So for the next 60 years we had 9 planets. Everyone grew up with the 9 planets. They could all recite all the orders that they were in, and they had all these different ways of remembering all the planets and everything. And then it changed again. In 1992 they found 15760 1992 QB1, which doesn't really flow off the lips, but so to its friends they call it QB1 for short. It's only about 160 kilometres across, so it's quite tiny. It's only, compared to the Earth, it's only about maybe that big. So it's very, very tiny. And it was a little bit further out than what Pluto is. You can see Pluto on average is about 30 times the Earth distance, and it's about 40 odd at its closest. These are the images for the Discovery. You can see they do the same thing as what they did for Pluto. They take pictures. It's very high tech. They take pictures and then they look at them some days later and go, anything move? And literally that's how they discovered them. Did anything move? And if you look carefully, you'll see that this little dot is slowly moving over in this direction, just very, very gradually. All these other smudges are all in the same spot. A lot of this stuff they can do by computers now, so they don't have whole groups of people looking at photos of millions and millions of dots, finding out which dot is the one that moved and discovering a new planet. So they kept finding more and more and more of these things. You can see some of them now have got names, but they just kept discovering them. They're all similar distance to what Pluto is, around 30 to 40 times the Earth distance. So they're all in the same region, maybe different locations around the sun, but all much the same distance. And also getting close to the size of Pluto as well, getting up to around 1,000 kilometres across. They know there's more than 1,000 of these things out there now. Some of them have names. Thankfully you don't have to memorise them, because Te Aroniawako is probably the most difficult to pronounce, or Rhadamanthus or something like that. Or some of them just have boring names like 2003 VB12. It's probably named after a beer or something, I suppose, I don't know. So they knew they had to do something because they were discovering more and more, and no one wants to try and memorise what are the 1,000 planets in the solar system, especially when some of them are names like Taironi Waco. So they had a meeting in 2006, and this is the meeting that all the people remember, only because of the outcome. They decided that they needed to have a definition of what is a planet. So they decided, first of all, it has to orbit a star. If it doesn't orbit a star, so it orbits another planet or something, then it's a moon. So that made that part easy. It has to be large enough to be round. So it has to be big enough that the gravity has made it basically round. So just some big random piece of stone can't be a planet because it's just a big random piece of stone. And it has to be basically the only one in that orbit. If there's a whole mass of them, then it can't really be called a planet because it's not big enough to muscle all the other guys out of its orbit. So if we put Pluto into this, yes, it orbits a star, and yes, it's very much round, but as you saw, there was a whole heap of other objects, similar distance. So Pluto's moving around out there, and there's all these other guys hanging around in the same area. So that's why Pluto was demoted to dwarf planetary status. However, Ceres was promoted. It's now a dwarf planet, so it's gone from a planet to an asteroid to a dwarf planet. So it's sort of one out of it, but not many people know about Ceres. So currently we've got 8 planets, and there's 5 dwarf planets. And then all those other things out there. But there's also other objects that you see in the night sky. It's not just these things that are orbiting like the planets in their own little orbits. Occasionally we're lucky enough, like we were back in 2006-07 with Comet McNaught. We see something truly spectacular and you can actually see it move from day to day, and it's not just a little dot in the sky that gradually moves. This is Hale-Bopp, which is one of the brightest comets. Unfortunately, it was only really visible in the northern hemisphere, but that was apparently even brighter than our McNaught. But it was in the northern hemisphere. The name comet is, comes from the Greek, which means long-haired, because when they saw these comets, they looked like some sort of an object, like a planet or something, with this long hair streaming off the back. And that's the terminology for why they call comets comets. They also saw them in the sky as some sort of a lot of races thought that they were like a sword from the gods, because they appeared to be this sword with this long tail. And so in most cases, most civilizations considered comets to be bad omens because they were associated with this sword in the sky or something from the devil or something like that. So they're always shown as messengers of doom. If you look at any engravings from the 1400s, 1600s or whatever, they always show this as a bad sign. Something evil is going to happen. A king is going to die. A war is going to start or something like that. Comets are basically large, dirty ice balls. Generally around 5, maybe 20 kilometres across. They're like a great big ice cube that's 20 kilometres across with a lot of dirt thrown in. And they travel in very, what they call eccentric orbits. So at one end they get very, very close to the sun and then they go way back out. They could go, in Halley's case, even out past Jupiter. It goes much, much further than Jupiter, and it comes all the way in closer to what the Earth is and goes around the sun and heads back out again. It takes 76 years to do that. Now they speculate that a lot of the water on the Earth actually came from comets, because comets are anything from 80 to 90% water. So if we look at a period of time from when the Earth first formed, about 4.6 billion years ago, up to the present, and we plot how many impacts. They do this, basically they do it from the moon, because the moon still has those impacts, and we assume that the number of impacts that the moon got, the Earth got pretty much the same number. And they can determine how old these craters are by various means. And so if they do this with the moon, they find that there was a lot of impacts 4.6 billion years ago, and then it died off, and then about 3.9 billion years ago, it kicked up again. There was another massive number of impacts of meteorites and comets or whatever at around about this time. This is a period they call the late heavy bombardment, and this is when most of the craters on the moon were formed, at about this time. And if they look at impacts from 4.6 billion years ago, there's very little evidence that there was any water, because that made a difference to the impacts, if there's any water around. And then when they look at the impacts from about 3.9 billion, there's a lot of evidence that there was lots of water around. So that's when they speculate that this was because all these comets were coming in at this period, bringing masses of water in. And that's when they think most of the water that's on the Earth actually got here as a result of all these comet impacts. Now, as these comets come close to the Sun, when they're way, way out past Jupiter, of course, it's freezing cold. As they come in closer, the Sun starts to warm them up. Because they're mainly ice and dust, this ice starts to warm up. So this one's heading towards the Sun in this direction. Then it heats up this material, the ice and the dust, and basically starts to make it, basically it evaporates. Pulls off little bits of dust with it, and it forms what they call the coma, which is like a head. So the actual comet would just be a tiny, tiniest little dot in the middle of this huge coma, which is all the material that's been thrown off, all this water vapour and dust and everything, which is much, much bigger than the actual rock that makes up a comet. And all this dust gets blown away by the solar wind. All this material that's thrown out by the Sun is literally like the wind, and it's just blowing this tail off the comet and blows it back into space for millions and millions of kilometres. These tails could be 20 million kilometres long, or more, much more. And some of the material also gets ionised from the Sun, and this creates an ion tail. So these are things that are actually charged. They've had electrons knocked off, and so they follow a slightly different path because they're charged. And as the comet comes closer to the Sun has this, what they call solar wind, is blowing out in this direction everywhere. So the dust is always blown away from the Sun. So even though the comet is coming around this way and the comet's travelling this way, the tail is still pointing away from the Sun. So towards the later part of its orbit, the tail is actually pointing away from the comet. So the comet basically is flying through its own tail because of this solar wind.